we're going to talk about fission. So fission is different. Fusion and fission. Now this can be very confusing for most students, right? Because it's only kind of one letter different. Fusion, if you're really good at remember, fusion is about combining two small things, okay? Fission is the opposite of fusion, okay? So what is fission? Okay. So some key terms as you guys are going through this. If you do not understand any of these key terms, please ask, okay? These are some vocabulary words. What is fission? Nuclei, okay? Nuclei is the plural of nucleus, okay? So instead of saying nucleuses, we say nuclei, okay? And that just means there's two separate nucleus, okay? And we say nuclei. Radiation. Radiation you've probably heard many times, right? Radiation is pretty bad. It hurts your skin. We're going to talk more about radiation next week and the different types of radiation. You are exposed to radiation every day, but not the worst types, okay? So we're going to talk about a little bit about radiation. Where is this seen? Fission is seen in nuclear power and energy. There is still a nuclear power plant here in California. It is down south. It was supposed to be closed down last year. They have extended that because they can't produce enough power elsewhere. So that is extended. I'm hoping, we'll see if we can. We'll see if we can get some of the engineers from the hydropower plant down here and PG&E to talk to you guys, hopefully sometime in the spring semester. It's pretty fun to talk to them. They can show you the different things that they do and what PG&E works for and the jobs that they all have. Okay. All right, so the step one of this one, again, you're going to use now. This one is kind of hard, right? Because you can see how big this atom or nucleus is, okay? Again, we're starting with step one, just like in fusion. We're starting with a collision. Every time we talk about reactions, it always starts with a collision of some kind, okay? Car crash. So you're going to put in your box, in your images, it starts with a collision, starts when a neutron, so pick a color for neutron, whatever color you want to use, collides with a very large atom or nucleus. So you don't have to count out and make sure that you get 92 and 143 neutrons. Just make sure you're putting in one color for protons, okay? One color for neutrons, and underneath you're going to write this one is uranium. So uranium is what they start in a nuclear reactor. They do use uranium. And some of the things you'll talk about, they may use plutonium as well, is another very large atom because it's on the bottom of our periodic table. Remember, our large atoms are on the bottom, towards the bottom of our periodic table. So it strikes, so a neutron, a free neutron, we call free neutron, strikes a very large atom, and it's very unstable. So some of our larger ones, they have a lot of neutrons. They're extremely unstable. They do not like to stay together, and we call them unstable eggs. You might hear some people talk about unstable eggs. That's what they're talking about. It's just a nucleus has a lot of neutrons in it and is unstable and wants to break apart. It's just shaking, okay? So plutonium and uranium are both those type of atoms. They are extremely unstable, okay? They do not like to stay together. If they have any interaction, such as a neutron hitting them, they are going to split apart. Okay. So go ahead and put this in your box and then fill in your notes for step one. All right, here we go. All right, next one, step two. So step two is what we call the division, okay? Remember in fusion, it was going together, right? Well, here in step two, they divide. So we start with a very large one, and after the neutron strikes the atom, they will split into two smaller, and this is where our vocabulary hits, nuclei. So that means there's two nucleuses or two atoms, that nuclei. And nuclei is plural for the form of nucleus. And then this is the image you're going to put in that box. So you have your neutron, okay? Then you have your large atom. The big thing when you're drawing this one is that you make sure the two that come off are smaller, okay? Because that neutron basically goes in and basically splits that large atom into two smaller nuclei. And what comes off is not just one now free neutron. Now we usually get 3 free neutrons that come out. So you can see here's a neutron, there's a neutron here. And then we have what we call a fission product. And we're going to add some nuclear notations to those in just a second in our next thing. But that's our step 2. So in step 2 of fusion, okay, they combined together. But in step 2 of fission, they split apart, okay? All right, so let's go ahead and move on to step 3. So step 3 is that portion of conservation of mass. This also conserves our mass. So notice now we're adding, we're going to draw these in, but now we're adding actual, so you guys can see the conservation of mass, adding in some nuclear notations, okay? So you can see how this works. So the first one you're going to do is draw out uranium-235. We're just going to use this as an example. Uranium-235, 92 is the atomic number of uranium. You're going to draw it out. Notice it's a much bigger nucleus than the smaller nuclei, okay? So make sure that first one is bigger, visually bigger than the next two, okay? So draw out uranium here, and just underneath it, you're going to put that notation 23592U. And then you're going to draw an arrow, okay? This is, if you want to label this, this is energy. We're going to talk about that again in a minute. Okay, and it's going to split into, in this equation, it's going to split into krypton, 9136. So it has a mass of 91. This is an atomic number 36, one of our noble gases, krypton. And barium, 142. So mass of 142, and a atomic number 56, barium. And then what also comes off are these 3, what we call 3 free neutrons, okay? So you can take those, so draw this into your box right now. Using the same colors you've used for your protons and neutrons from your other 2 boxes. All right, so let's learn about the step 3 conservation of mass. So, okay, what we see here is the number of protons are conserved during the reaction. So how do we know that? Well, remember that atomic number represents our number of protons. So if we start with 92, then all of this should add up to 92. So if I add 36 plus 0 plus 0 plus 0 plus 56, if you add it together, you get 92, okay? So the amount of protons are conserved. What it started with in uranium shows up in all of the products, okay? We're going to practice this today, okay? So as you can see, the krypton of 36 plus 56 barium will get 92 from uranium, okay? So when you add up the protons that come out, or that are products, they should equal back to the atomic number of the nucleus that you began with, okay? They cannot disappear. They don't just go poof. They have to be from somewhere, okay? All right. All right, next one. All right, this is step 4. So this is adding that energy. And so you can see this one, all this is showing it's starting to split. So again, you've got uranium, and we're going to do this one at uranium-236, 92. And it's going to split into energy is what's coming out in this one, step 4. So in step 3, we have that conservation mass. Everything kind of splits up in nuclei, and then we get that burst of energy. This is where nuclear gets the energy that runs our lights and everything here in California. And if you look at Europe, they actually use a ton of nuclear energy in Europe because they have small amounts of land that we have more land, so they use more nuclear over in Europe. Nuclear has a bad rap. It's said that it's unsafe. There are times it has been unsafe, but actually there's less accidents in nuclear accidents. They're just worse than in normal coal burning, okay, which we still do here in the United States. So what comes out is 236 units, and then we get krypton, barium, we get 3. So this is, instead of drawing out those 3, I'm introducing you guys to the notation. If we have more than 1 neutron, how do we notate that? And notice we're just going to put a number 3 in front. So instead of writing plus 1 0 neutron, plus 1 0 neutron, plus 1 0 neutron, we just write the 3 in front, and it's 1 0 neutron, okay? To show that there's 3 neutrons that come out, okay? And so we call this a coefficient. So this is your first introduction to what a coefficient inside an equation looks like. And it just means there's 3 of those neutrons there. So draw this into, make sure you're adding that energy in there. Now we're getting that burst of energy, okay? So when it splits, because it's unstable, when it splits, all that energy is released. Because remember, we also have to follow the conservation of energy. Okay, energy has to go somewhere. So if it had energy, it's got to come out. Okay, and if it's coming out, do you remember, is that endothermic or exothermic if it's coming out? Exothermic. Okay, so this again, the same as in fusion, is an exothermic reaction. We will feel the heat. This is why nuclear power plants are extremely hot. That's why these uranium tubes that they have are actually, we have time on Friday, I'll show you the video of going through into a nuclear reactor. They have a little video and you can kind of see what it looks like. It is down inside water, okay? But when that overheats is when we've got a problem, okay? All right, so let's look at energy, what comes out. All right, so a large amount of heat is produced, heat energy, okay, which is a nuclear reactor is converted, and then they convert all that heat and energy into power, which they send to us through all their lines, okay. How big is it? So this reaction, remember, fusion released 800 million evolts. This only releases 200 million evolts. So, which means if they can get fusion to work, they will produce 4 times the energy in one single reaction. Okay? And your barbecue puts at 50 evolts. Okay? So, it's a lot. It's very, very hot. You don't want to be near it when it's going on. Okay? So, yes, PG&E still owns 1 nuclear plant here in California. And it is down south. It's near the ocean. They like to have them near the ocean because when this thing heats up and gets too hot, they got a lot of water to cool it down. Because they need to cool it down, and they need to cool it down fast. Okay? But they've never had an issue with the one here in California. All right. Oops, this way. There we go. All right. What this does, and this is probably the hardest one, you don't have to add all the notations. If you want to, that's fine. But what this does, and this is why a nuclear reactor can get out of control, okay, if they're not watching it, okay, they have to really pay attention, is in this picture, you're going to start with a big one, which then splits into 2 small ones, okay. You get those free neutrons, right? Well, those neutrons are what started the reaction in the first place, right? It hit that unstable big old nucleus. So now instead of 1, now I got 3. Those 3 go find uranium again or plutonium, whatever they're using. Now we're going to get 3 of them that are going to split. So we call this the chain reaction because we get the first one to split. Then we get 3 to split, right? Now we get 9 to split, 12 to, 18 to split, and it just goes from there. So you can see, and each one of these reactions is a split second. We're not talking about minutes. We're not talking about hours. We're talking about seconds. Okay? And it causes this huge chain reaction, and each one of these releases energy. So you're releasing 200 million evolts each time you split. So you can see when they put one of these small little rods, these aren't big, if we get to the video, hopefully we do on Friday, it's a tiny little rod that they put in there and it goes. And it's just a complete chain reaction. Okay? And they have to be able to control that temperature because you are releasing a ton of heat and energy. If it gets overheated, that's when we have a meltdown. Okay? Inside a nuclear reactor. Okay? So go ahead and draw that into your box there for your chain reaction. All right, so let's fill in kind of the written part of this. All right, so the neutrons produced, so the neutrons that are produced in that first fission reaction that come apart, so you have one that hits it, and then you have those three that are produced from that one fission reaction can cause or create further reactions, right? That's what that chain reaction means, okay? And so radiation, so we've talked a little bit about radiation. We'll talk more about it next week. It's caused by those free neutrons. It's not caused by the energy coming out. It is caused by the neutrons that are just sitting there. So when these chain reactions are all done, when there's no more big nuclei for those neutrons to hit and split apart, they're just hanging out. And so what happens is that is the radiation that hits your skin, and that causes now your atoms to split apart, okay? Which causes a problem inside your body because now you're breaking down the atoms that make up your skin, your blood vessels, your heart muscles, okay? So those free neutrons are causing this fission reaction kind of in your skin, and that's what causes your skin to deteriorate because they need certain atoms, right, to survive, okay? You need certain carbon, oxygen, and so forth to survive. So these free neutrons is what's causing it. It's not the energy and the heat. Okay? It is hot. You will get very hot and burned by it if you're near it. Okay? But the radiation is actually caused by all those free neutrons that are produced. Okay? All right. Questions. What starts a nuclear fission reaction? A proton, an electron, or neutron? Which one starts a fission reaction? A neutron, yes. So a neutron, okay, is what starts a fission reaction. Okay. And then when is energy released in this reaction? So when does energy come out? When the atom splits? At the start of the reaction or at the end of the reaction? What causes that energy to come out? What is happening when that energy is released? Which one? When it splits, right? Because remember, when it splits, okay, when that atom splits, remember it's an unstable atom. So it's really shaking and it has a lot of energy inside of it. And when it splits, it's going to more stable nuclei, okay? And that energy has to go somewhere. It's not going to go back in because then it's unstable again, right? So it's going to come out, okay? It's going to come out. All right, go ahead and put these notes into your notebook, okay?